For Lab 3, we will look at three main concepts when identifying the entire scope of the black hole. First, we will create an orbit. Second, we'll find the mass of the black hole. And third, we will address a hypothetical situation where a spaceship was approaching the system simulated in part 1 with the main goal of just not crashing into the black hole. So for our forces from motion, the general approach to finding the forces from motion between the star and the black hole begins by first identifying the system, which in this case is the visible star near the black hole. After that, we will observe the code in Glowscript to find the net force on the star. We then will specify interactions such as the gravitational force of the black hole on the star, and finally solve for the unknown mass of the black hole. On the right is my code for the net parallel force, net perpendicular force, and net force. After some tweaks and testing, an arrow scale of 2 times 10 to the negative 17th produced the most accurate arrows, as seen here. So the star with a mass of 2.0 times 10 to the 30 kilograms is orbiting a black hole of unknown mass, as shown by the black dot. The orange arrow shows the net force, which is always pointing towards the black hole. The magenta arrow shows the net parallel force, initially pointing in the path of motion, and the blue arrow shows the net perpendicular force at a 90-degree angle to the net parallel force, always pointing towards the center of the kissing circle. Here's a continuation of the diagram. So in order to find the mass of the black hole, as previously mentioned, if you knew the mass of the black hole and the mass of the star, you would calculate the net force on the star by the black hole using F net equals gravity times the mass of the star times the mass of the black hole over the magnitude of r squared, and then proceed with the rest of the calculations involved in the gravity net force equation. If we were to calculate this by iterations by hand, it would look like the bottom left, or repetitive calculations using each position to find each change in velocity, to find the change in position, to find each net force. It is much more efficient to just use the Glowscript code to perform the iterations for you using a while loop. On the right, I copied the Glowscript code into an Excel sheet to show each of the iterations I showed from the beginning and then a snapshot from the end. So my final average black hole mass came out to approximately 1.89 times 10 to the 34th kilograms, and F net came out to approximately 1.00892 times 10 to the 29th. Delta P over delta T equals F net parallel plus F net perpendicular, which is the same as F net by the momentum principle. The parallel values and the perpendicular values in the net force and the momentum align. The change in momentum is found by analyzing the system's motion. However, in other words, a change in momentum is caused by the net force, so they are not the same things. If you decide to enter into an orbit around the black hole, I found that my spaceship would need to have an initial velocity of negative 20.24 times 10 to the 6th in the x-plane and 8.7 times 10 to the 6th in the y-plane in order not to crash into the black hole or the planet. And here's a snapshot of the actual code for that process.